Okay, we do another hypothesis testing problem. This one, again, we will use the p-value method for evaluation for deciding whether or not to retain or reject the null hypothesis. For this problem, we have a small sample of 6 replicates. The mean pH of the sample is 6.68 with a standard deviation of 0.2. Can we conclude that this is indeed less than mean pH of 7? Now we'll use the method, t-test for doing this. Before doing so, I should point out that we should be fairly confident based on previous work of some sort, that the original data is approximately normally distributed before proceeding. We'll just make that blanket assumption so that we can do this, but that assumption needs to be made that the original data at least approximately follows the bell curve. Okay, so in doing so, the null hypothesis will be that the mean is equal to 7, and the alternative hypothesis will be that no, it's not equal to 7, the mean is indeed less than 7. And we have our test statistic t, and this will be set up as usual, that it's the observed average minus the sample average divided by the standard error for the average. And we have 6 replicates, so square root of 6. Okay, so we plug this into the calculator. So I'll use a calculator for this demonstration. And we get 6.68 minus 7 divided by 0.2 divided by the square root of 6. And so we get a t-value of negative 3.919. Now that's a fairly negative number, but we also have a very small sample. So to use the p method, we will determine what's the probability of seeing an event this extreme or more extreme. So I have a t distribution, and I have 5 degrees of freedom, 6 minus 1. Now in this case, extreme means I shade to the left. And as always, the part that gets shaded is going to be dependent on what the form of the alternative hypothesis is. Here I have a less than, and so I shade to the left. If I have a greater than, I must shade to the right. And if it's a not equal, I actually shade both tails, and then so basically my answer gets doubled. Okay, so the p-value is going to be whatever the area is under the curve there. Now this can be done using Excel, using the t.dis command that we discussed in class, using a calculator, so I'll do that here. The command is going to be tcdf, and the commands are going to be left endpoints. So my left endpoint is basically minus infinity, so left endpoint. My right endpoint is the thing that I just got, so that's my answer. And then I input the number of degrees of freedom. So this is going to be a little bit different than the normal CDF command on the calculator. It has, like the normal CDF command, we have a left endpoint, right endpoint, but my third argument is the number of degrees of freedom. So when I hit enter, I get the area to the left, which works out to be 0.0056. Okay, so if I believe the null hypothesis, and I believe that that the mean pH is 7, then I also have to swallow the fact that something that only had a 0.56% chance of happening just happened. And that works out to be 1 chance in, well, let's work it out. So 1 divided by the answer. Something that only had 1 chance in 178 of happening just happened. And so my conclusion is, and I'll type out the conclusion. So our conclusion is that we reject the null hypothesis. It appears that the mean pH is less than 7. And so that would be the conclusion that we make based on the data that is available to us, because the p-value is less than alpha. Now, as before, this could be done with critical values. The critical value that we get cannot be done on a calculator. However, using Excel, we can figure out the critical value. So the critical value would be t.inv, left-tailed inverse. Standard assumption is that alpha is 5% unless I say otherwise, 5 degrees of freedom, and we get negative 2.01 to be the critical value. So the critical value would have been about over here at negative 2.01 or so. And on this side, we reject the null hypothesis. Whereas on the other side, we retain the null hypothesis. And so the decision we make is consistent with the decision that we would have made using the critical value method. One other observation that I'd like to make is that the technology will actually do this kind of test, and I want to show you how that can be done. The test on the TI-83, we press the Stat button. We go over to Tests and then T-Test. And in this case, I'm going to be inputting statistics. If I actually had the hard data, I could input the data. In this case, I have the summary statistics. The null value is 7, but my sample average is 6.68. My sample standard deviation was 0.2, and my sample size is 6, and I have a null hypothesis, or an alternative hypothesis that has the less than form. And so when I hit calculate, the test actually does exactly what we're talking about. The t-value is negative 3.919, as we had before, and we get the p-value of 0.0056. So the test statistic matches, the p-value matches, and I believe that gives everything. And so from here, we would make the decision based on our preference of the value of alpha as to whether or not to retain or reject the null hypothesis. So it does not compute the critical value, at least not on the TI-83, but it does compute the p-value, and so from this we could make the decision. Microsoft Excel has the similar capability with the command t.test. However, for that command to work, you actually need to input the raw data. I don't believe that works with summary statistics like we just did with the calculator.